Hi again, everybody. Here is a video that's going to help with using the segment addition postulate. So we're going to attack this part here. I can use the segment addition postulate to find the lengths of segments. Okay? So basically the segment addition postulate is just a fancy way of saying little plus little make big. What does that mean? Well, if you've got a point in between two other points, literally in between, well then that makes a little segment here, a little segment here, and then a big segment that combines the two. So when I say little plus little make big, I literally am saying this little piece plus this little piece makes this little piece. Or excuse me, it makes the big piece, sorry. But B has to be between them for that to work. How about over here? E technically is not between D and F because it's not actually on the line. It has to be collinear in order for it to be between. So while I understand you might, in your heads, you're thinking, well, if I just extend D here and extend F here, well, then E is in between. But how do you extend a point, right? A point is just that single dot. So this one you cannot use the segment addition postulate, but this one you can. So here's where it's summarized for you. If B is between A and C, just like it is here, then AB plus BC must equal AC. Little plus little make big. All right, so here's the equation for it, and you're going to basically use that every single time. Sometimes they're going to give you the two little ones and you have to find the big one. Sometimes they'll give you one of the big ones and one of the little ones and you have to find the other little one. And sometimes they don't give you any of them and you have to use a little bit of algebra to figure it out, and that's what we're going to practice here. So we'll do a couple different kinds of examples and hopefully it'll make sense as we do them. So here you go. Example number 1. Segment PR, okay, right? Segment PR, there it is, segment PR. Q is between P and R. Now, just because it says between doesn't automatically mean it's smack dab in the middle. You could almost look at this and say, oh, it looks kind of like it's in the middle, but there's no guarantee. So unless you know for sure, you cannot assume that it's in the middle. You just put between. So like, look at this one actually, this is a really good one. B is still between A and C, even though it's not even close to the middle. And I'm saying that relatively speaking, it's not even close, it's still kind of close. But I'd say this one's a lot closer. The point of it is, no pun intended of course, the point of it is it doesn't actually matter as long as it's in between. Alright, so PR is 16. PR is the whole thing, right? PR is literally the whole thing. That's 16. They're giving me that. I know PQ is 9 because they gave me that too, and we need to find QR. So when I look at this, I'm seeing that they gave me the big, I know one of the littles, and I have to find the other little. So here we go. PQ plus QR equals PR. That is the segment addition postulate in perfect form here. I know PQ is 9, so I substitute that in. I know PR is 16, so I substitute that in. And then of course I solve, just subtract 9 from both sides, subtract 9, and there's your 7. And that's the basic idea behind the segment addition postulate. We can apply it in sort of a real world setting here, sort of, a little bit of a stretch, but here we go. We've got this segment SD. The locations lie on a straight line. So we know this is on part of a line. I know it only is a segment at this point, but it's SD. They're telling us we have to find the distance from the starting point to the destination. So they actually want us to find the big. Well, lucky for us, they gave us both of the littles. So since R is between S and D, SR plus RD must equal SD. So when you set up your equation, all you're doing is really plugging in, which values that you have, and then solving for the one you don't have. So I'll substitute 64 for SR, I'll substitute 87 for RD, and of course that equals whatever that total is. Looks like 51. So that's 151 miles. And that is the distance from S to D, from starting point to destination. All right, last couple here. They actually gave us the diagram. Everything's labeled for us nicely. They don't always do that, but in this case they did. And we have to find KL. Again, KL by default is the distance from K to L. So I know big is 38, I know one of the littles is 15, and I already know some of you are thinking, Mr. Miller, can't I just subtract them? Of course you can. All right, if you want to write it like this instead, 38 minus 15 equals the KL, and then figure that out, absolutely, totally fine. Totally fine. Oops, sorry, it got cut off. There you go. If you want to write it this way, I have no problem with that. But if they tell you, use the segment addition postulate and, to write it out the original way, I guess you could just write it like this, equals JL. And that would be, a good way to start, especially if you're not sure what to do. Then you start substituting in and you'll realize you're going to end up subtracting anyway. All right, this one is probably the most tricky when it comes to solving, just because they don't actually give you as much information as they did in the other ones. The good thing is, since t is still between s and v, I can do the same thing we've done on all the other ones. Little plus little must equal big every time, and just start substituting until eventually you get what you're trying to solve for. ST is 20 plus TV is n must equal SV, this whole thing, is 2n minus 1. And now hopefully you look at that and you recognize that as, okay, I need to solve algebraically. Doesn't really matter which part you do first, as long as you get all your variables on one side, all your non-variables on the other side, and solve. It doesn't really matter which way you go, so I'm just going to add 1 to both sides to start. So that's 21 plus n equals 2n. Now I'll subtract n from both sides, so 21 equals n, and I believe we're done. N must equal 21. Let's make sure we answer the question. Use the diagram to find SV, so they actually want the whole thing. 20 plus 21 must, of course, be 41. If at this point you see that and you're like, you know what, but what about the 2n minus 1? Aren't I supposed to do something there? Well, if n is 21, you can substitute it over here too. And no matter which way we do it, we should get the same thing. So let's do that over here. 2n, which is 21, minus 1. That should also equal SV. Either way, it should work. So this is 42 minus 1. And 42 minus 1, of course, is 41. And we got the same thing both ways. 41 over there, 41 over here. We know we did it right. And that is an algebraic example of the segment addition postulate. All right, hopefully that helps. Feel free to rewind and rewatch and ask questions, whatever you need to get through the practice problems. And hopefully it'll all work out for you. And I'll talk to you guys later.